This is part 2 of lecture on least squares approximation, section 7.3 from Math 311, a course of linear algebra at Western Illinois University. And of course I should say this is part 2. Okay. Alright, so we talked about, talked a little bit about this linear regression problem and how to find a line given a given set of points that are scattered throughout the plane. How can we find a line that best approximate them? So that is, we want to find a line so that maybe not all these points lie on the line, maybe none of them do, but we would like the combined distances of these error gaps, these gaps, to be as small as possible. Okay, where so if we have these points x1, x2, x1, y1, x2, y2, and so on, we can define this, like this first error is just the vertical distance from a point to the line, whether that point is above the line or below the line. So what this is it's going to be basically the y coordinate of this point minus the y coordinate of this point, or vice versa. Because we're going to be squaring it anyway, so the sign won't matter. But then the y coordinate of this point would be a plus xi plus b, and then the y coordinate of this point would be yi, or in this case y1. So then we can define epsilon I to be this, to be the ith error, and then we want to find a and b such that the combined the sum of these squares is minimized. Okay, so we want to do this, and in fact this is just going to be the what the expression, the sum that we have right here is specifically the square of the length of the vector sum ax minus b, where A is this matrix where we have 1s in the first column and the x coordinates in the second column, and then B consists of the y coordinates, and then X just consists of A, B. And again, this comes from the fact that ideally what we want is A, or I should say, A plus BXI to be equal to YI, okay, for each Y. So we get A plus BX1 equals Y1, through A plus B xn equals yn. This won't have a exact solution, but we want to minimize. We want to find the A's and B's that make this the gap between to make these as close as possible, and that's what we're talking about, the least square solution. And if we recall, the least square solution, if A is an m by n matrix and B is a column vector of length m, the least square solution to the equation ax equals b is this vector we call x bar, such that the length of ax minus b is minimized, or the distance between ax and b is minimized. And we found out that last time that x bar satisfies this normal equation, we get A transpose A times x bar equals A transpose times b. And if this matrix is invertible, we can compute it this way. We can multiply both sides by the inverse of A transpose A, and we get an explicit formula for x bar. Okay, and that's the least squares solution. And that's what we're really, in this case, the least square solution is in fact this AB. If we find it, we'll find the coefficients of this regression line, okay, which is what we want. All right, so we did an example last time. I'm going to do another example this time. I will just say one thing, that in this case, there are other ways to handle this. Maybe even if it's not invertible, we're still solving a matrix equation. We have some matrix times x equals a column vector. That's what this essentially is. So this might have, if this matrix is invertible, there's a unique solution, but there might be, in other cases, if it's not invertible, we might have many solutions. All right. So, yeah, and we know there are lots of ways to solve this equation. Okay, so what we'd like to do now is do this first example. We want to find the linear regression line for these 3 points, 2, 1, 1, 4, and 6, 0. Okay. And so again, we're trying to find a line given by y equals a plus bx. And then where a plus b times, in this case 2, is equal to 1, a plus b times 1 is equal to 4, and a plus b times 6 is equal to 0. That's what we really want to find. We want to find the a and b that solves the system best or closest. So the corresponding matrix is this. It's just 1, 1, 1, 2, 1, 6 times the vector AB equals 1, 4, 0. Okay. So this is our A, this is our X bar, and this is our B. Okay. So we can go ahead and proceed. We can first compute A transpose A, which is A transpose is 1, 1, 1, 2, 1, 6. And A is right here. Okay. If we compute this, this turns out to be a 2 by 2 matrix, which is given by 3, 9, 9, 41. Incidentally, this matrix is always going to be symmetric, right, because it's a matrix times its transpose. And now, because this is a 2 by 2 matrix, we have a nice formula to find the inverse of this. So we're just going to use that. You can check that the determinant of this will be 3 times 41 minus 9 times 9. That turns out to be 42. And so the inverse of A transpose A is 1 over 42 times 41, 3, and this is negative 9 here. All right, so we have that formula, that explicit formula for 2 by 2 matrices. Okay, and I'm just going to keep the fraction out here to keep, to postpone the fractions of this solution. So now we know that x bar then has to be this inverse. Okay, times A transpose times B. Okay. This is should be a 42. Sorry about that. And I'll just save you the calculations. You can do these. I put off the fraction to the end. This is 1 over 42 times 151 negative 27. Okay. I'll let you compute these two, and then multiply this one, and you'll get this. So we get that A is 151 over 42, and B is negative 27 over 42. Okay, so that so the regression line would be y is equal to 151 over 42 plus, or I should say minus 27 over 42 times x. Okay, now let's suppose if we wanted to actually compute the error, and what was by error we mean the length of ax bar minus b. Okay, well, we just go ahead and compute it. What we do is a is still 1, 2, 1, 1, 1, 0. That's a. X bar is this 151 over 42 negative 27 over 42, and then we want to subtract b, which is 1, 4, 0. Okay. So that's ax bar minus b, and then we want to take the length of that. Okay, and so what is this going to be? Let's first take the square of this first, and then we can take the square root. So what will this be? This, if we just take the corresponding components, so this is going to be the length of the vector 151 over 42 plus or minus 227 over 42 minus 1. Then this is going to be 151 over 42 minus 27 over 42 minus 4. And then finally this is 151 over 42 plus 0 minus 0. Oops, I'm sorry. This is a what did I do wrong here? This should be a 6. Yes, 6. So this is going to be minus 6 times 27 over 42 minus 0. Okay. So we compute this number and square it, we compute this number and square it, we compute this number and square it, add it all up, and then this turns out to be approximately 2.88, and so the actual error is the square root of that, which is approximately 1.697. Okay. So okay, so that was here. We found out what x was. Now we just plug this in and compute this. Okay. All right. Now let me give one last example where we can see that this applies more than just doing linear regression lines. We can actually use this process to define any polynomial curve to approximate some points. Okay, and particularly we can do it with a parabola. So let's say we wanted to find a parabola that best approximates these 4 points. Now for 3 points, we're almost always going to have an exact solution. Okay, so let's just do 4 points. And what we're really talking about is here's our parabola, and let's say here's our points. And again, we can still talk about this vertical distance between the points and the curve, and we these would be our epsilons, and we just want to minimize the sum of the squares of those errors. Okay, so let's do that. So we're trying to find a parabola that approximates this. So ideally, we would like to a parabola that passes through all of these. And if that's the case, then in this first point, the first point 1, 1, means that a plus b times 1 plus c times 1 is equal to 1. 0, 3 means that a plus b times 0 plus c times 0 squared is equal to 3. The point 2, 3 means that a plus b times 2 plus c times 2 squared is equal to 3. And the point 3, 5 means that a plus b times 3 plus c times 3 squared is equal to 5. Okay, now what this means, matrix-wise, what this means is that we have this matrix. We have 1, 1, 1. That's because it's 1 times A plus 1 times B plus 1 times C. And here we have 1 times A plus 0 times B plus 0 times C. So it's 1, 0, 0. Then here we have A 1 times A, 2 times B, 4 times C. And here we have 1 times A, 3 times B, and 9 times C. Okay, this times A, B, C is equal to 1, 3, 3, 5. All right, so that is the matrix equation AX equals B. We're trying to find, so we want to find the least square, so ABC represents the least square solution of this. Okay, where this is our A, this is our X, and this is our B. Okay. All right, so once again we compute A transpose times A. So this will be 1, 1, 1, 1, 1, 0, 2, 3, 1, 0, 4, 9, times 1, 1, 1, 1, 0, 0, 1, 2, 4, 1, 3, 9. And you do the calculations. This time we get a 3 by 3 matrix, which is 4, 6, 14. 6, 14, 36, 14, 36, and 98. All right. Now, we could go ahead and take the inverse of this. You could do that. If you don't want to, I don't blame you. Let me just show you a slightly different way of doing this. Let's compute the other, if we recall, we just found this matrix. We can compute this matrix, and now we'll just have a single matrix times X to equal a single column vector. And maybe that might be nicer. Let's see. So A transpose B would be this matrix. Times 1, 3, 3, 5. And this turns out to be 12, 22, 58. Right? So basically we just need to solve this matrix times X equals this. So we have 4, 6, 14, 6, 14, 36, 14, 36, 98 times ABC is equal to 12, 22, 58. All right. Again, we could try to take this matrix, or I use Cramer's rule. You can use Cramer's rule. Or, just find the inverse directly. If you use Cramer's rule, you're going to have to simplify this. So what happens is when you do that, you get that A is equal to 14 fifths, B is equal to a negative 11 fifths, and C is equal to 1. So the parabola that you want is actually y is going to be 14 fifths minus 11 fifths x squared plus, or not x squared, just x plus x squared. Okay. So that would be the parabola that best approximates this. All right. So a lot of calculations here, but hopefully you can see the basic strategy. Set up your matrix, find what A is, compute A transpose A, and then it's just we reduce it to a slightly easier, not more easier, but one more familiar problem of just solving a matrix equation. And I'll let you work on the exercises, and I'll see you next time.